Chapter number 6, Ampere's Law. In this chapter, we are going to cover the topic of magnetic field and its application in a new form of the potential vectors for the magnetic field. The topics are going to be like this: Biot-Savart Law, Ampere's Law, Divergence and curl of the magnetic field, Application of Ampere's Law, and magnetic vector potential. Biot-Savart Law. Stationary charge produce electric field that are constant in the time. Steady current produce magnetic field that is also constant in the time. Current which arises due to the motion of the charges are the actual source of the magnetic field. When the charge move in a conducting wire, produce the current I. Magnetic field at any point P due to this current can be calculated by adding up the magnetic field contribution dB for small segments of the wire ds. This segment can be taught as a vector quantity and having a magnitude of length segments pointing in the direction of the current flow. Infinitesimally small current source can be written as IDS. Let R be the distance from the current source to the field point where we wanted to find the magnetic field. And r cap vector is a unit vector in the direction of r. The Biot-Savart law gives the expression for the magnetic field as dB equal to mu naught RDS cross product with r cap divided by r square, 4 pi r square, where mu naught is a constant called permeability of free space, having a value of 4 pi into 10 raised to minus 7 Tesla meter ampere. Adding up these contributions, small contribution, we will find the complete magnetic field at point P due to the wire having a current I. Therefore, we will take the integration over the current source. As you can see from the figure, B is equal to integration of dP is equal to mu naught divided by 4 pi integration IDS r cap divided by r square. This is the Biot-Savart law. But if we wanted to find the Biot-Savart law due to the surface current source, therefore, for surface current I is equal to integration K times dl, where K is the surface current density. If we substitute this K dot dl value in the place of I in equation of B, then we will have mu naught divided by 4 pi K cross r cap divided by r square dA prime, where dA prime is actually result of dl dot ds, line segments. For the volume currents, the Biot-Savart law becomes for the volume current I equal to integration of J vector J is the volume current density dot dA. Now if we put J dot dA in the equation of Biot-Savart law in place of current I, we will get J dA dot ds cross r cap. Now dA, that is area, dot ds, that is length. This make volume, and here we have a prime volumes. This is what we have learned Biot-Savart law. Now, second topic, Ampere's law. The statement says that the line integral of the magnetic field around any closed path equal to mu naught times of net steady current enclosed by the path. Where we write the statement into the mathematical form, integration over a closed line dB dot dl is equal to mu naught. Magnetic field produced by the straight long conducting wire is we have known to have B equal to mu naught I divided by 2 pi r in the direction of phi. Any arbitrary line segments considering the cylindrical coordinate system along a closed path is given by dl equal to dr r cap plus r d phi cap plus dz k cap. If we multiply d B vector, magnetic field vector B with dl, we will get mu naught I divided by 2 pi r. R cap r phi cap can cancel because it's a dot product. We know that r cap phi cap equal to 0 since they are not same. But phi cap is 1, r d phi, and k cap phi cap is also 0. If we take the closed line integration of the above equation, then we will have mu naught I divided by 2 pi integration over a closed line d phi. Now, this closed line d phi is nothing but total circle 2 pi. If we replace that with 2 pi, we will get integration over a closed line b dot dl is equal to mu naught I. And this is the integral form of Ampere's law. Therefore, the derivative form of Ampere's law will be, now current I stand for total current enclosed by the integration path. If the flow of charges is represented by the current density, and here we will take as a volume current density, therefore the enclosed current I is equal to integration J dot dA. Applying the Stokes theorem on the left hand side, we will get integration over closed line B dot dl is equal to integration del cross B dot dA. And replacing I with integration of J dot dA. Finally, that result into del cross B is equal to mu naught J. This is the derivative form of the Ampere's law. Divergence and curl of magnetic field vector B. First, divergence. Now consider a volume V prime that containing a non-uniform current distribution J. The magnetic field for the general case of volume current density is mu naught B is equal to mu naught divided by 4 by integration J cross R cap divided by R square over the volume d tau prime. Now this formula gives the magnetic field at the point P, this P, X, Y, Z, in terms of the integration over the current distribution, that is J, which is the function actually is the function of the prime, X prime, Y prime, Z prime, that is the prime volume. Then we have to think about some few points. First, B is the function of unprimed coordinate, that is X, Y, and Z. Whereas the volume current density J is the function of the prime coordinate, that is X prime, Y prime, and Z prime. R prime is the position vector of volume d tau, whereas the R vector is the position vector of point P, X, Y, Z. Therefore, R cap is actually the vector difference of R minus R prime, that is X minus X prime, Y minus Y prime, Z minus Z prime. Now d tau is dx prime, dy prime, and dz prime. The integration is taken over the prime coordinates, that is on the volume V prime, but the divergence is taken with respect to the unprime coordinate, that is x, y, and z. Taking the divergence of B, we will obtain del dot B is equal to mu naught divided by 4 pi integration del dot J cross r cap divided by r square over the volume d tau prime. Now, if we take consideration of integration term del dot J cross r cap divided by r square, here if we expand this formula, we will get r cap divided by r square dot del cross j minus j dot del cross r cap divided by r square. Now this second term is completely zero because r cap divided by r square is a gradient of 1 upon r. That's why curl of a gradient always zero. Therefore, we have del cross r cap divided by r square equal to 0. Now, this del cross j is 0 because j does not depend upon the unprime coordinate variable where we are taking the curl or divergence with the with respect to the unprime variables x, y, and z. Therefore, we conclude that L dot B is equal to 0. That is, divergence of a magnetic field is 0. Curl of magnetic field. Applying the curl to the magnetic field B, del cross B is equal to mu naught divided by 4 pi integration del cross J cross r cap divided by r square over the prime volume d tau prime. Now, taking the integration term outside del cross J cross r cap divided by r square and expanding the equation, we will get J del dot r cap divided by r square J dot del r cap divided by r square. The second term automatically gets 0 as it is a prime or unprime coordinate. About the first term, that is del cross r cap divided by r square. Now this term is nothing but 4 pi drag delta function in 3 dimensions. If we place this value into the equation del cross b, therefore del cross b is equal to mu naught divided by 4 pi integration j vector j 4 pi drag delta function r minus r prime d tau. That means j vector is when on the prime coordinates, we will find the del cross b. That is equal to mu naught j at the prime. Now, application of Ampere's law. In this topics, we will see three basic application of Ampere's law. Out of this, first is magnetic field produced by straight, long conducting wire. Now, magnetic field at a point depend upon the distance of the point from the wire. Further, field is tangential to the circle of radius r and its direction being given by the right hand rule. Thus, the integration over a closed circle around the circle is b equal to integration over closed db dot dl is equal to, when we take b outside, integration over closed length d dot 2 pi r. Now what we know from the Ampere's law in the integration form, integration over closed path db dot dl is equal to mu naught I. If we replace d 2 pi r in place of integration over closed path db dot dl, then it is equal to mu naught I. That means b is equal to mu naught I divided by 2 pi r. Second application, but it is in a y direction. Okay. infinite solenoid. Now, a solenoid is a long coil of wire tightly wounded in a helical form. If the turns are closely spaced and the resulting magnetic field inside the solenoid becomes fairly uniform, provided the length of the solenoid is much greater than its diameter, for the ideal solenoid, which is infinitesimally long with the turns tightly packed, the magnetic field inside the solenoid is uniform and parallel to axis and vanish outside the solenoid. The cross-sectional view of an ideal solenoid is shown in the figure. To compute B, we consider the rectangular path of the length L and the width W and transverse the path in the counter and clockwise manner. The line integral of vector B along this loop 1, 2, 3, 4 is integration over closed path dBdl is equal to integration over the path 1 dBdl, integration over the path 2 dBdl, integration over the path 3 dBdl, integration over the path 4 dBdl. As we have already discussed, there will be no magnetic field outside the solenoid. Therefore, for the path 1, it is equal to 0. And for the path 2, magnetic field direction and the dl direction are perpendicular to each other, that is 90 degree. Therefore, the second comes to the 0. Accordingly, similar way we will find for fourth part, as the dl goes from 3 to 1 and the magnetic field is perpendicular to dl. They are sharing or they are perpendicular to each other, that is 90 degree to each other. Therefore, fourth paths result to the 0. Only third part, where dl and dp match with each other, we will find the magnetic field, that is B times L. Now this B times L in total is equal to the total current enclosed by the Ampere's law, that is I enclosed, and the number of turns, total number of turns, capital N. Therefore, the applying Ampere's law, we yield integration over closed path dBdl is equal to 3pl, which is equal to mu naught n times of I. Therefore, B is equal to mu naught n times of I divided by L. Now, n by L is small n, number of turns per unit length. Third application is toroidal coil. Let n number of be the total number of turns in the toroidal ring, and let r is the distance radius of toroidal ring. B is constant along the circular path. Then integration over closed path dBdl is actually equal to B, since it is uniform along the closed path, in dot 2 pi r, circumference of the toroidal, is equal to mu naught n times of I. Therefore, B is equal to mu naught n I divided by 2 pi r. This is the magnetic field equation for toroidal coil. Now, final magnetic vector potential. As a divergence of magnetic field yield to 0, this shows that B is a curl of some function. Let that function to be a vector potential, that is del cross A, where A is called vector potential. As the divergence of a curl vector is always 0, so we can say this. Now for the Ampere's law, in the derivative form, del cross B is equal to mu naught J. So in place of B, if we write del cross A, therefore we will get del cross A is equal to mu naught J. If we open this del cross A, we will get gradient of del dot A minus Laplace of A. Now, divergence of del dot A is 0. Since we have already considered for before definition of this vector A, that it is a function of curl, it's not a function of divergence. That means del dot A is 0. Therefore, this term is first term becomes 0, and we will get Laplace del square A is equal to mu naught J. Now, integrating each side and using the solution of Poisson's equation, assuming J goes to the 0 at infinitely, we will find the value of A, which is equal to mu naught divided by 4 pi integration J divided by R over the volume B tau prime.